Good evening and welcome to the second event of the Cosmic Zoom exhibition. This is a new outreach initiative organized by the ICTS. And today we have Professor Biman Nath, an astrophysicist at the Raman Research Institute, Bangalore, speaking to us about an exciting topic about the discovery of helium that happened in India about 150 years ago, which actually marked the beginning of modern astrophysics. Professor Biman Nath is an astrophysicist at the Raman Research Institute in Bangalore. And his research involves the study of the interaction between galaxies and diffuse gas in the universe. He has also written several articles and books on popular science, both in English and Bengali. And apart from these very interesting popular science books and articles, including the one bearing the title of today's lecture, Professor Nath has written fiction. In particular, his first novel, Nothing is Blue, has received critical acclaim. This is a fictional work that combines history, astronomy, and mathematics. As we will soon see, Professor Nath is an excellent teacher and an engaging speaker, and I assure you that we are in here for a treat. So let me once again invite Professor Nath for all of us. Biman, please go ahead.
Thank you, Ajit, for the kind introduction and the invitation to speak at this event. So let me share the screen, right? That's right. And let me know if this is right. So I'm going to talk about helium and the discovery of helium in particular. Helium happens to be the second lightest and the second most abundant element in the universe, by which I mean, if you look at the periodic table of elements, helium nucleus has 2 protons and 2 neutrons, as opposed to the hydrogen nucleus having only 1 proton. So if you look at the periodic table, helium is the second element, which is why it's the second lightest or second heaviest. It is also, if you notice that it is also positioned extreme right along in with other elements in a column that has neon, argon, which we all recognize as inert elements, noble gases, because they're chemically inactive. Helium, although it's rarely found on Earth, it is actually found everywhere else. And if you look at the total mass inventory of the whole universe, we find that it's the second most abundant element after hydrogen. So this is the pie chart of all the elements that appears in the periodic table. So about 3/4 is made of hydrogen, and slightly less than 1/4 is made up of helium, and less than about 2% of all the elements. All the other elements comprise about less than 2%. The interesting thing about helium was that it was the first element that was discovered by astronomers and not by chemists. And its discovery was a unique event in the history of science, and it gave rise to a totally new field of science, which we call astrophysics, and that's the story I'm going to tell today. And what makes it interesting is that the story of its discovery is somewhat blurred in the collective memory of scientists, science historians, and not just blurred, it's somewhat distorted, I should say. And so what I would like to do is to tell you the story of actually what happened, the actual story behind the discovery of helium. To give you an example of the mistakes in the popular account, let me quote from Encyclopedia Britannica. How do I take this? Okay, right. All right, let me quote from Encyclopedia Britannica on the topic of the discovery of helium. It says, to quote, in 1868, while observing an eclipse whose path of totality passed over India, the French astronomer Pierre Janssen observed a bright yellow line in the spectrum. Janssen noticed, and I have underlined it and with highlighted with red color. Janssen noticed that the yellow line's wavelength was slightly shorter than that of the well-known line of sodium, and he reported his result to the British astronomer Joseph Norman Lockyer, who had missed the eclipse. Well, that is wrong. But the last sentence is particularly wrong. Another example. During the ceremony of awarding William Ramsay the Nobel Prize for the discovery of noble elements, including helium, in 1904, the president of the Royal Swedish Academy of Science said this, to quote, the existence of helium was demonstrated by Janssen during a spectroscopic examination of the solar chromosphere in 1868 while making an observations on an eclipse of the sun in India. This is wrong, by the way. The only science historian who said it explicitly that Janssen did not discover helium, but this appears in a French article in a French journal in 1999. So that's what is more is that there was another person involved with the story of, I'm trying to get rid of this, all the thumbnails of the people, and because it's sort of blocking my view of the screen. Can't seem to do this. Okay. But there was another person involved whose contributions have been almost completely forgotten, and that's the story I would like to tell you. So let's begin at the beginning. The story of helium begins with the discovery by Fraunhofer in 1814, when he discovered from this a monastery near Munich that when you look at the solar spectrum, the spectrum of the sun, so you pass the light of the sun through a prism, and we all know that it breaks up into different colors. You see all the colors from blue to red, but you also see some dark lines superposed, and this is a postage stamp commemorating his discovery. And this was a very intriguing discovery, and physicists actually struggled to explain the cause of these dark lines for about half a century. So their clues came from different observations. Like a few years later, John Herschel and other at Talbot, they noticed that different substances gave rise to different set of bright lights. Then in 1830, Brewster superposed the spectrum of the sun and the gas in the lab, and he saw that the few dark and bright lines seemed to coincide. So there was a postulate that one could probably infer or identify the substances in the sun from their spectrum, because the spectral signature, the bright lines, the wavelengths of the bright lines, or the dark lines in the Fraunhofer, they are saying something about the identification of the elements. But the origin and the cause of the dark lines remained a mystery. Foucault probably came closest to an explanation in around 1849. Yes, this is the Foucault, famous for the Foucault's pendulum. It's a picture I have put on the right-hand corner that you'd see in Ayuka in Pune, Foucault's pendulum. So what he did an experiment in 1849. He passed electric current through an arc, and that produced light. And he noticed that the light, when you look at the spectrum of the light from this arc separately, you see a bright yellow line, which is coincident with a dark line in Fraunhofer's spectrum. And let me show you the Fraunhofer's spectrum again, and because this is going to be very important. So he had marked these lines at A, B, C, D, and so D line, what he called the D line, falls in yellow. And actually, this is a doublet line. There are two lines which is too close here, so which is why it's written. It's a bit thick here. So there are two lines, and you call them D1 and D2. So these are called sodium D lines. And why sodium, I'll tell you later. So what Foucault noticed is that if you look at the light from the electric arc, you see a bright line at the same position where Fraunhofer had seen a dark line in yellow. And then he did something else. He passed the sunlight through the arc and took a look at the spectrum, and he saw that the dark line got enhanced. And so he said that the arc presents us with a medium that emits the D rays of its own account, and which at the same time absorbs them when they come from another quarter. Okay. Ultimately, so Foucault was a very versatile scientist, and he was very interested in many other things. And so he soon left the topic and started working on lenses. But he mentioned these ideas during a dinner at Cambridge with Stokes, and Stokes told it to Lord Kelvin. So there was a buzz in the air about these ideas. But ultimately, it was solved in 1859 by Gustav Kirchhoff and Robert Bunsen. What they said is this. So if you look at, so this is Kirchhoff and Bunsen. So if you look at the light from an element, suppose you burn an element, some material, and look at the light from the burning of this element, of this material, then you will find in the spectrum a set of bright lines at different wavelengths, okay, that will determine their colors. And if you put this element in the path of another bright light, then you would find dark lines instead of bright lines, and the lines would be at the same positions. So this is to quote Kirchhoff: the dark lines originate from the presence of these substances in the solar atmosphere, which cause bright lines in the same place in the spectrum of a flame. So his idea was that this dark lines was caused by material in the solar atmosphere, which is relatively cooler than the solar core from where the white light is coming, which comprises of all the colors. And this material, which is relatively cooler in the solar atmosphere, is absorbing, which, if the material had been hot, and if we could see the material, if we could burn the material elsewhere, then we would have seen bright lines at the same position. Right? This was slightly difficult theory at that time. And in 1859, Kirchhoff came up with a theoretical paper stating the thermodynamical basis of his ideas. There's a story that there was one day they saw that there was a fire in a forest in Mannheim, which was some kilometers away from their laboratory, and they happened to turn their spectroscope to that fire, and they could identify the sodium lines and a few lines. And so for example, they had passed an incandescent light through flame with sodium and saw dark lines. But then sun doesn't have any dark lithium lines, but when you pass the sunlight through a flame with lithium, it shows dark lines. So they started asking the question that does it mean that we can identify what is there in the sun? That, for example, it has sodium but not lithium? And so, as I told you, there was a forest fire, and they turned their spectroscope towards that fire, and they could identify a few elements based on what they had seen in their laboratory. And apparently Bunsen said, if we could determine the nature of substance burning in Mannheim, why couldn't we do the same for the sun? Kirchhoff apparently said, Bunsen, I've got mad. And Bunsen also said, so have I, Kirchhoff. Anyway, this is from an article in Nature. So in this way, they could infer the presence of hydrogen, magnesium, calcium, nickel, copper, etc. So this is from their original paper in 1859. By the way, 1859 was a watershed year for science in many ways. That's the same year where when Charles Darwin published his book, Origin of Species. So here was a new way of identifying elements, and not just identifying, discovering new elements also. And soon they discovered cesium and rubidium in the lab. William Crookes in England discovered thallium. And so the face of chemistry had changed with this new idea from physics. And well, as I said, 1859, Kirchhoff then developed a mathematical theory of absorption and emission in equilibrium. Sometimes you see dark lines, sometimes you see bright lines. So he set out this idea: when would you see that? Which one? And he proved that mathematically that the emission in the spectral line is proportional to the absorption in a dark line, and the ratio of emission to absorption is universal. He also thought that this leads to a theoretical construct of a substance which we can imagine that it absorbs all radiation falling on it. But then it also means that it is also going to emit all colors. We call it a black body. And so Kirchhoff's idea was that black body radiation is universal. It depends only on temperature. So this is the spectrum of black body, which depends only on temperature. At different temperature, it peaks at different wavelengths, which is why, for example, if we heat up iron, it first looks red and then orange and then yellow as it gets hotter and hotter. At any rate, but his theory was so difficult, it had few takers. And let me give an example of some of the criticisms that he had to face. So, for example, this is an editorial. I'll not tell you the name of the editor. I'll just show you the picture. I'll tell you later because he's one of the heroes of the story of helium. So in Chemical News, published from England, 1861, the editorial said, "We consider this law incapable of supporting the actual discoveries with the least cogency and to be untenable, notwithstanding the fact that it has generally been acquiesced to." There was a Jesuit priest in Vatican, Father Angelo Secchi, who I'll tell you more about him later. So he said that we wanted to say these things less to object to such an distinguished physicist than to prevent science from taking a retrograde course, especially since history shows that persons of great authority in one branch of knowledge often drags along under the weight of their opinion those who are less experienced. These are pretty bitter remarks. And the reason why Kirchhoff's idea was, people found it very difficult to accept that Kirchhoff's solar model was very different from the prevailing model at that time, which was due to William Herschel, the discoverer of Uranus, by the way. So according to Herschel's model, the core of the sun is cold and dark, and the surface is hot, which is luminous and bright. And for example, this is a picture of the sunspot. So how do you explain sunspot with Herschel's model? He said that, well, sunspots are basically the places where there are holes in the surface, which allows you to peek at the cold and dark core of the sun, right? And now Kirchhoff came and then he said, no, it's the other way around. The core of the sun is hot, which is why it is emitting bright light. And the solar atmosphere, the outside, the surface layer, is relatively cold, which is why it is absorbing and producing all the dark lights. Right? It was totally different, which is why people found it difficult to accept his ideas. But there was one testable prediction of Kirchhoff's model. And this is what makes science interesting, right? I mean, you produce a model, you advance a model to explain some observations, some results, but then you also predict new results, which then scientists go on to test whether either confirm or refute. That's how science progresses. Now, the the Kirchhoff's model, there was one testable prediction, is that somehow if the very outer layer of the sun, well, it is relatively cooler to the solar core, but it is hot. It's now we know that it's few thousand degrees hot. And Kirchhoff said that if you can isolate the light of the very outer layers of the sun and look at its spectrum, it should show bright lines, not dark lines. In other words, the dark lines of Fraunhofer should reverse if the spectrum from the outer layer could be isolated. And that's the only, right? And the only way to test this idea was during a total solar eclipse, when the bright disk of the sun would be hidden by the moon, right? Now, where was I? So, and at that time, there was, interestingly, there was a news that indeed a total solar eclipse was in the offing a few years later in 1868, and the totality would be of that of 6 minutes, which is pretty long compared to typical eclipse durations. And there was a paper from a Major James Francis Tennant, who was in the East India Company Army, belonged to the Bengal sappers, but he was mostly working with the Great Survey of India, and he was working on the east-west grid, mostly working on the western side. By the way, he is the person who first determined the coordinates of latitude and longitude of Karachi. He was then in 1857 he was actually brought to Delhi, and he had to fight in. He took part in a crucial battle in Kashmiri Gate. Then what happened is that while working with the survey, he developed an interest in astronomy, also on the theodolite, the instrument that surveyors used, which is very close to in structure to a telescope, and he got interested in the working of the theodolite. Those days, the telescopes were balanced by hanging additional weights, which he found cumbersome, and he designed a way to relieve the pressure through fluids. And this became a cornerstone of modern telescope design, where pressure was relieved through mercury-filled tanks. Somehow his name is not mentioned anymore, but at that time, his ideas were appreciated. Anyway, so he came to, after the 1857 mutiny, he was sent to Lucknow to help lift the siege of Lucknow at the residency of Lucknow. And then he wrote a paper, another paper in monthly notices, the report on the Nawab of Awadh observatory. This is a good place, by the way, to mention the interesting thing about the new field of astrophysics, about the practitioners of this new science, who were mostly amateurs, and that's because of the fact that, first of all, this new field required skill in photography, chemistry, in addition to regular astronomy, and which didn't really fit the regular program of the observatories and professional astronomers. Also, there was this prevailing philosophical idea called positivism, which said that it's futile to engage in the research of what was called insolvable problems. And one example that was given is that you should not attempt to learn the chemical composition of the sun or the distant objects, stars, for example, because they will forever be inaccessible to us. And so it was futile. And so this was a very, this ideas influenced scientists a lot. So what happened is that this void was quickly filled by a number of what you can call risk takers, or advanced parties scouting, distant frontiers. And also the regular astronomers scoffed at these new practitioners of new science called astrophysics. Otto Struve once said that God forbid that astronomy should be carried away by fascination with novelty and diverge from the essential basis of positional astronomy. You see, at that time, astronomers were mostly interested in the position and the movements of objects in the sky. They were not interested in what stars were made of and the physics of stars, for example. And that's what started astrophysics. Right? And so enter a bunch of people. So this is sort of collage of these people. So I've already talked about James Francis Tennant. There was Warren Delarue on the right-hand side corner. He was a paper manufacturer who became interested in astrophotography and became a pioneer of astrophotography. I've already talked about Father Secchi. I'll tell you more about him later. There's Norman Lockyer. So let me read it out. So this is a quote from John Langford, and saying that the new specialty of astrophysics did not develop in the university context. Astrophysical studies often started outside established observatories. The problems that astrophysicists initially sought to explain placed a premium on the design, construction, and the manipulation of complicated research equipment rather than on theoretical knowledge. And here was a field where amateurs might excel. And so here is the picture of William Huggins, who gave up a business in silk and set up an observatory in his house and became a pioneer in stellar spectroscopy. And here's a picture of his wife, and they both conducted observations. And here is a quote from his diary. Nearly every observation revealed a new fact, and almost every night's work was red-lettered by some discovery. You know, the lack of their professional knowledge in science was, made up by or compensated by their passion, in a way. There was also, this is Norman Lockyer. We'll hear more about him later. He was a clerk at the War Office in London, started writing popular science articles. And when he moved to Wimbledon, he had a neighbor who had a telescope, and he was greatly impressed by the sight of the sky through a telescope. And he bought a telescope on his own and started doing observations and writing papers on the moon and Mars. And then he met Huggins once and became interested in spectroscopy and started to do spectroscopy of the sun himself. There was Father Angelo Secchi, who was a Jesuit priest, and he basically learned astronomy while in US as an exile. As you know, during a French occupation, the Jesuits had to leave Italy. Anyway, when he came back, he was given the charge at the Vatican Observatory. See, at this time, the nationalists in Italy, they were complaining against the clergy, saying that they were not modern enough. So the Pope at that time wanted to show that, he was also interested in science, and so asked Angelo Secchi to modernize the observatory. And Secchi took the opportunity to install various instruments, including a spectroscope. And then in 1863, he had a young visitor from France. His name was Jules Pierre Janssen. He had problems walking because there was an accident when he was a child. The nurse had accidentally dropped him. So he couldn't go to school, he couldn't attend school, but he managed to get a PhD on the optics of the retina. He didn't get a job, a regular job of an astronomer at the Paris Observatory, for example. And the director of the Paris Observatory at that time was the co-discoverer of Neptune, an old-style astronomer. But he managed to find friends in the French Academy and got some grants and went to places. I mean, although he had difficulty walking, he went to Andes Mountain in South America, to Alps, doing all kinds of scientific experiments. He also designed and manufactured a spectroscopy which had the highest resolving power at the world. By the resolving power, I mean the ability to separate out lines of different elements, different wavelengths. Okay, and so he went up the Alps, looked at the Fraunhofer lines with the variation of it, and it's found that there was variation in the Fraunhofer dark lines, which and he inferred that some of the lines in the Fraunhofer set of dark lines were due to atmosphere. We call them telluric lines today. At any rate, the news of the upcoming eclipse in 1868 made the European astronomers all interested in sending teams to Southeast Asia, because the totality belt was going to cross the Southeast Asia, especially India. India offered the best vantage point, but the timing was very bad. It was going to be August, is the monsoon month, and so the weather was an uncertain issue. Johnson also became interested. So he convinced the Academy that the 1868 eclipse is going to be important, and then he wanted to see whether the dark lines in the solar spectrum reverses at the outer layer, and if it does, then Kirchhoff was going to be proved right. But the powerful lobby at the Paris Observatory, they planned to send a team to Thailand, because the king of Siam was somewhat more sympathetic to them. And the French territory in India, the Pondicherry, it was out of the totality belt anyway. And the French team didn't even consult Janssen. So Janssen, he managed to get a separate grant from the academy and decided to go to India alone. I mean, he was quite a resourceful person and quite an adventurous person. This is a picture, by the way, of 2 years later, 1870, when there was a eclipse in Algeria. And from France, he wanted to go to Algeria to observe the eclipse, but there was a siege of Paris by the Prussian army, so he was not allowed to go. So he just ascended, he got a balloon for himself and got on a balloon and to cross the army posts. Just to give an example how adventurous he was. At that time, William Huggins argued that, well, we don't really need an eclipse. All we need to do is to isolate the outer layer of the sun. And he thought, well, if you look at the outer layer of the sun, it is reddish. And he thought that maybe if we use a red filter, maybe we can isolate the outer layer, but he failed in that idea. Lockyer noticed that, see in this picture, that there are what we call prominences. There are solar storms which rise from the surface of the sun. Now we know better. And so there are prominences, you can see, and they are red in color. And suppose one could put a slit, by which I mean a narrow window, through which you basically let light pass through your spectroscope. So light from only that region will be allowed to enter the spectroscope. That's what we call a slit. So Lockyer argued that if we can put a slit on one of the prominences, then it's fine. We don't need an eclipse. But you need to know the position of the prominence to begin with. And in his language, one has to fish around. So at any rate, he got a grant from the Royal Society to build a bigger telescope. But it so happened that the telescope maker fell ill. This is the summer of 1868. And so he was left without a telescope. At that time, in the meantime, Major Tennant, he received a grant from the Royal Astronomical Society to organize an eclipse team with telescopes, photographic plates, because photography had just been tried. The first photography of eclipse happened just 7 years before this. So people were excited to try this out again. But definition so that you could take multiple photographs during an eclipse, and they had only 6 minutes. So Tennant, being an army person, he came up with a system of drills with his assistants to take as many photographs as possible. There was John Herschel. I showed the photograph earlier in one of the slides, who was the son of William Herschel himself. And John Herschel had 2 sons at that time living in India. Younger son happened to be in Bangalore. was also named John Herschel Jr. By the way, his the eldest son was in Bengal at the time, and he was studying on his own a very interesting topic, that of fingerprints. And he would be writing in later 19th century a paper in Nature, which on fingerprints, the uniqueness of fingerprints. Anyway, Herschel asked his younger son, who was stationed in Mangalore at that time, to organize another expedition and to ask him to focus on spectroscopy. While all this was going on, there was another astronomer uh, in India who was watching all this in silence and agony. This is Norman Pogson, who was basically a self-taught astronomer who had apprenticed with an instrument maker in Manchester, and then after which he got a job in Radcliffe's Observatory in Oxford as an assistant astronomer, where, by the way, he worked on a method of measuring the brightness of stars, which we still use today. This is the magnitude system, and that's due to Pogson. But he never got a regular job, and science historians have different ideas. One of the ideas is that maybe he didn't have any degrees from Cambridge or Oxford, without which it was very difficult to rise in uh, science in England. But he got a job as the government astronomer in 1861 to join Madras Observatory. When he landed in India, so his original idea was to catalog the southern hemisphere stars, survey the southern sky. But when he came here, the royal astronomer at that time, George Airy, asked him not to pursue this. And from this point on, their relation went downhill, and Pogson started, this is the original building of the Madras Observatory, by the way. And he started complaining about his salary, his projects, his assistants, whom he called, described as most adults, machines without the certainty of machinery. The living condition, so this is taken from one of his reports. He's writing, first observation in India taken in the compound in happy, fearless ignorance of snakes, centipedes, scorpions, and all the filthy, dangerous vermin abounding in my new home. Right. He had a very colorful language. Anyway, so he, by the way, all his reports of the 1868 eclipse was never published in any peer-reviewed journal, whereas everybody else's accounts were published in peer-reviewed journals. When in 1868, his wife was suffering from cholera, and she would soon die. And he finally published his report on his own initiative, on his own. Anyway, he organized an expedition team on his own with engineers from telegraph, from railways, and he managed to get a spectroscope from William Huggins. And he was watching, all the other European astronomers getting good grants, and so he wrote, "I have never been able to comprehend the peculiar ground upon which European observers justify the needless and lavish expenditure." He chose, by the way, Machilipatnam in the totality belt. This is on the coast, because he didn't have any extra grant to go anywhere, but he was also the meteorological officer of India at that time, in addition to being the government astronomer. And there was a severe cyclone 4 years before this in Machilipatnam, which took thousands of lives. And so there was an idea that Machilipatnam should have a weather station. So he used this pretext to go to Machilipatnam, set up a weather station, and maybe also observe the solar eclipse. At the same time, Tennant and Janssen, they chose Guntur. This is away from the coast. Well, it's a very small town at the time. Not many people, and even the officers, British officers, would not like to actually go there or spend many years, because the weather was bad. And anyway, I thought I'll quote from a book from Frankenberg, who's a social scientist and expert on the colonial life in Guntur, and quoting a widow of a collector's widow who remarked on the boring social life in Guntur. After dinner, the company all sit around, talk in whispers, and scratch mosquito bites, talking about promotions while ladies gossiped about ayahs and scandals. And you can imagine how the small town took on a totally new appearance with the astronomers descending on the town. Tennant got a lot of help from the government officials. His sketch that I had sketched from the original sketch of Tennant's team in the compound of the house of the sub-collector of Guntur. Janssen, as usual, he proved to be very resourceful. He found a rich French tobacco merchant in Guntur. There was a flourishing tobacco business, by the way, in Guntur. And that house happened to be the tallest in Guntur and also had a terrace. But it so happened that when Janssen landed in Madras, by the way, Suez Canal was still not open, so he had to go all the way around Africa. Well, I mean, if he had come today, I think he would have been stuck at the Suez Canal, given the traffic jam there. Anyway, when he landed in Madras port, he found that his luggage had been misplaced. I couldn't find most of his instrument, but he had his spectroscope with him and the small telescopes that he had carried. So he could bring them to Guntur. So that's then August 1868. The eclipse was going to start at 9 a.m. The totality would start at 10. It was early in the morning, so the sun would be fairly low on the sky. So, and it so happened that there was morning mist in that day, and that made the astronomers very worried. But when the eclipse started, the mist cleared away, and here's a picture taken by Tennant's team. They started taking. So initially they thought they would do a dress rehearsal, and one of the calls was mistaken for the actual eclipse, and so there was some problem with the coordination, but they managed to take 6 snaps in 6 minutes. But although the clock drive, which was fitted to the telescope, this is a 9-inch telescope, to track the sun, that failed. So they had to do everything manually. Given all that, the picture quality was pretty good. At Machilipatnam, Pogson had to worry about a totally different problem. He wrote in his report that there was a crowd had gathered in his equipments who were too inquisitive and meddlesome loiterers, not contented with looking, must finger the thermometers and tamper with the instruments. He always had colorful language, you see. Janssen and so everybody saw the bright lines. So Kirchhoff's idea was proved right. Everybody saw bright lines. Janssen saw it, Tennant saw it, and Herschel also saw it. And they all thought that it was due to sodium, the sodium D line, right? In fact, Herschel wrote that there's no question that the orange line was identified with D, except Pogson. He was not so sure. He thought that the line was either coincident or very near D. I have underlined very near. I'll tell you why, because that was very crucial for the discovery of helium. And this is the hand-painted spectrum from Pogson's report, which you can find in the archive of the Indian Institute of Astrophysics in Bangalore, Koramangala. Janssen was thinking of something totally different, by the way. He thought, well, he had seen the prominence. So he thought of trying to put his slit on the prominence the next day when there would be no eclipse. This is the idea that Lockyer had, right? But Lockyer still didn't have his telescope, but Janssen did. And so he thought of trying this out next day, and he hardly could sleep that night. He woke up at 3 a.m. But he was successful and saw the bright lines without the eclipse, right? So he called it a perpetual eclipse, and he sent a telegram to Paris. By the way, there was a telegraph line which had just been opened through Iran and Afghanistan by the Siemens company, and there was a telegraph office at Vijayawada. So he sent a telegram, and then he decided to study this in more detail before sending a detailed report on 19th September, from Kakinada. He sent a letter to Paris, after which he went to Calcutta and then to Shimla, and actually tried out an instrument which is the precursor of what we call spectroheliograph today. Anyway, Lockyer in England and others heard about this discovery, but Lockyer could get his telescope only on 20th of October. And that immediately he didn't go to his office that morning, and immediately tried putting a slit and the prominence, one of the prominences, and saw the bright line spectrum, and including a yellow line near D. And he sent a brief report to the French Academy. So I have written about these details of the story. You'll find this in this book that I've written. Okay, and of course I talked about Janssen. And these two letters, these two telegrams, one sent from India a month before this, and one sent from London on 20th of October, both of them arrived at the French Academy in Paris on 24th October, within a few hours of one another, which was a very dramatic event. And so the French Academy decided to declared them joint discoverers of a method of studying the solar spectrum without an eclipse, not about the discovery of helium, please note. Then Lockyer went on to discover chromosphere, that the red layer around the sun. But he found many enemies in England because of his aggressive nature. He started collaborating with a chemist, Edward Franklin, who was the father of the valence theory, which we all learn in school, by the way. And the idea was to find an element or some material which could give rise to this extra line, which we started calling D3 line, to distinguish it from the D1, D2 of Fraunhofer line due to sodium. And the Franklin thought maybe hydrogen under different circumstances would produce this line, and then they started doing experiments. Although Lockyer thought maybe that's a sign of a totally different element altogether, and he named it helium from Helios. Franklin, by the way, objected to this hypothesis, and later he wrote, "I remember always protesting about this yellow line, about this assumption of a new element." But if you look at, if you read the account written by Charles Young, an American astronomer who wrote in 1896, I'll quote, "Most of the observers of the 1868 eclipse, by the way, supposed it to be helium line, but Janssen noted its non-coincidence. Franklin proposed for the new substance a provisional name of helium. Everything's wrong. Franklin did not propose it. Franklin, in fact, opposed the idea." Okay. In fact, the only accurate account of this event comes from Subramaniam Chandrasekhar, who wrote in 1947, referring to the yellow line. Pogson said that it was at D or near D. Almost the whole of the story of helium depends on this distinction. And that's the crux of the story, by the way, and that only Chandrasekhar wrote about this clearly. By the way, Charles Young, this American astronomer, there was an eclipse in 1870, which was visible from North America. And he saw a bright green line, which he called, okay, it's also from maybe another new element, which he called coronium. By the way, Pogson had seen this green line back from Machilipatnam, but nobody took notice of that. In fact, some started suspecting that maybe helium and coronium are the same element. And there was a huge confusion when William Huggins reported another line from a planetary nebula in 1864. which he called nebullium. Okay, this is Cat's Eye Nebula, Draco, and this is where William Huggins saw this line. And then D3, this line, was discovered in a nova in 1876. Also, this is the green line. The confusion became even more when a geologist reported to have seen the helium line from a substance that he said he collected from during an eruption in the Vesuvius in 1881, but he didn't preserve the sample, so he could substantiate his claim. And there was a lot of problem with the priority, after the actual discovery of helium. Okay. And D3 line was being seen then from a lot of other places, from Orion Nebula in 1886, right? So there was this idea that helium, of course, helium, only Lockyer thought of helium, but this D3 line, whatever gave rise to D3 line, was everywhere else. And there was also this idea from William Prout, which we all learn in schools, for example. The weights of atoms are integral multiples of that of a fundamental element. Initially, they thought of hydrogen, but there was problems with the non-integral weights of chlorine, for example, which is 35.5 times the weight of hydrogen, which we now know is because of different isotopes of chlorine and the relative abundances, etc., etc. But there was the idea of isotope didn't exist at that time, so there was a problem. And so Lockyer suggested that spectra of elements depend on temperature, and atoms possessed more elementary form at higher temperature, which you would find in nebula. Well, I mean, in hindsight, he was true. There's some grain of truth in what he said. I mean, we know that the atoms become ionized at high temperature. And he said that matter evolved and cooled from this primal matter in nebula to stars. And helium could be this primal matter. And if helium happens to be lighter than hydrogen, then this idea of a non-integral weight would be also solved if helium happens to be have the half weight of hydrogen, right? So there was this idea. And William Crookes, for example, gave a lecture in 1886 on this. He said, for him, the primal matter could be a formless mist, a substance with the potential of becoming and evolving into atoms. But William Crookes had some bad reputation at that time of attending seances and defending so-called mediums and spirits. So this is a picture of William Crookes with one of the mediums at that time. So nobody took Crookes this idea of Crookes very seriously. And there was a criticism from none other than the high priest of chemistry, Mendeleev, who had been invited to England to give the Faraday lecture in 1889. And he really criticized the astrophysicists in very harsh words. He says, astrophysics is still for want of laws at the epoch of accumulation of facts, not of their. Okay. Pretty harsh words indeed. But he was interested in observing total solar eclipse, and there was a eclipse in 1887 over Moscow. He went up alone in a balloon, but it was a cloudy day, so nothing happened to it. But I must mention that even in 1903, after the discovery of the noble gases, Mendeleev actually suggested that there were two more noble gases, newtonium and coronium, which was seen by Pogson and Charles Young, by the way, and that they had atomic weights less than hydrogen. This is Mendeleev's paper, okay? And you can read about this paper in a paper named Article Mendeleev as a Speculator in 1981. Anyway, Janssen, by the way, at that time, this time had moved away from spectral analysis, and he had come to India in 1871 during another eclipse, and he found a very interesting correlation between corona and sunspots, which were very important. And then he became interested in photography, and he got the idea from the Colt's pistol, right, a revolver, of that of a photographic revolver, what you call a photographic revolver, which became a precursor of the cinematography. So he became a pioneer in cinematography, and this is, so he went to Nagasaki. Let me pause this. And then he went to Nagasaki in 1874. He was really a globe-trotting scientist, if there was one, ever one, during a Venus transit. And with the help of what he called the photographic revolver, he took moving images. And this is probably the first movie you can say. And this is about sort of the Venus transit. The Venus, you can see crossing the disk of the sun. I'll show this movie again. It's amazing. And so he became a pioneer, and his pioneering efforts in cinematography was appreciated. By the way, this was there was a conference 1895 in Lyon, and Lumiere brothers shot a movie with Janssen arriving at the conference. This is Janssen, by the way, arriving at the conference. So Janssen had moved away from the study of the spectrum of the sun. By the way, 1895 is the year when helium was discovered in lab, and that happened because of well, I'll come to this later. Pogson by this time had died in 1891 in Madras, largely ignored by his peers in his later years. He was not considered for the new observatory at Kodaikanal, because William Huggins had written pretty critical remarks on for Pogson. This is you'd find the tombstone. Norman Pogson. He was buried in Madras. By the time, at that time, there was a lot of competition between Huggins and Lockyer. They were fighting about over nebulium. So Lockyer thought he had, since he suggested helium as a new substance, nobody else should. So he said, nebulium is not a new line, it's a new element, it's basically magnesium. And so there's a nasty war of words. And Huggins at some point wrote to Hale, as an American astronomer, to quote him, "These attacks of Lockyer are giving us much pain. It's difficult to keep them from eating out of our lives all joy." It so happened that there was a geologist from US who had made a rather mundane discovery of finding nitrogen-like gas from a sample of uraninite, and it showed some unusual spectral lines. And he wrote a paper in 1887. Nobody noticed it for 8 years until it was noticed by a mineralogist in British Museum who told Lord Rayleigh and William Ramsay, because they were looking at atmospheric nitrogen and the inert gases, and that led to the discovery of all the inert gases. And so Ramsay then immediately collected the gas from a sample of a similar mineral called cleveite, and then asked Crookes to look at the spectral signatures, and Crookes immediately confirmed that yes, it is the helium line. And so helium was finally found on Earth, was discovered on Earth, and Lockyer wrote in Nature. By the way, Norman Lockyer had founded the journal called Nature, and he was the first editor. So he wrote in the editorial, the 26-year-old helium had at last been run to Earth. D3 was at last visible in a laboratory. But still, the drama was not over. By the way, there was a Swedish team who had almost simultaneously and independently came to the same conclusions, but they decided not to pursue this priority debate. And although Ramsay acknowledged their efforts, their contributions in his Nobel lecture, but there was a problem with when Runge and Paschen, they claimed that the helium line was not single, that there was actually a double line. And Huggins wrote to Hale, the helium plot thickets. And Lockyer immediately wanted to name the other element, which he thought, it's a different element, so he had to name it also. And he suggested asterium, but he was dissuaded by others. Much later, when the advent of quantum mechanics, when people understood the structure of helium, we realized that there was the two types of helium, depending on the relative spins of the two electrons that the helium atoms contain. One is called the perihelium and orthohelium, and the spectral signatures are different. I'm not going to get into that. So this is the story of helium, the discovery of helium. And but before oh, it's already 8 o'clock. I'll just quickly say this, that why, I just also wanted to understand why do we have such distortions in science history? Why do we have myths like this? Research is never done individually. I mean, it's usually a multi-participant activity. And so eureka moments are often myths. So the story that we hear about Galileo's dropping, doing this experiment from Leaning Tower of Pisa, actually never happened. That story was spread by one of his juniors after Galileo's death. Benjamin Franklin never actually flew a kite. That story has been debunked. And so why are there myths in the science history? One reason is that we tend to see things from the viewpoint of the present, which was called, has been called presentism by Stephen Jay Gould. And it tends to favor the successful researchers and ignores the other practitioners who have not been so successful. We also tend to prefer a linear story than a nonlinear narrative, right? Because science is never linear. There are blind alleys, the false sense, the dead ends, and John Waller has written that they're all overlooked. Sometimes scientists also, distort the story to throw people off the scent to something embarrassing. I'm not going to tell you the details of the story of Joseph Lister, who created a myth around himself about the cleanliness in hospital, but which is in reality, it was way too different. There's also the tendency of, we always romanticize the past, right? That tends to the distortion of science history. And so what I think happened with the helium story, two things has happened. One is that the coincidence of the two telegrams from Lockyer and Janssen arriving in Paris at the same time, and they were friends. There were no dispute over priority, which was very, very unique. Very different from the all the other debates over priority between Newton and Leibniz, and we know how scientists tend to claim their contribution, and they were good friends, by the way. So Janssen and Lockyer, so it has the key requirements of a good story for romanticizing the past. So what they did has been largely forgotten, except the fact that they discovered something together, which is why you tend to see even now saying that the helium was jointly discovered by Lockyer and Janssen, where it was not. Also, astrophysics had moved on, and their actual discovery was a matter of distant past, when helium was really discovered on Earth. By the end of 19th century, astrophysics went out of the realm of amateurs to professionals in large observatories. So what they had done, people had largely forgotten what they had actually done. So there were all the ingredients for romanticizing and distorting the history is all there, and that's what has happened. And so now we know that research has become even more multi-participant. There are large collaborations. So I often wonder, have we entered an age of science which is devoid of myths? Because as John Waller has written, that there's much less scope for one individual to shine like the moon among stars these days. When research is mostly done in like assembly-like manner, and so these great stories have become rare events. So I'll stop there and take any questions.
Thank you very much, Biman, for this really exciting.
I'm sorry about exceeding the time. So yeah.
No, not at all. And this is a really remarkable combination of science, history. So the floor is open for questions now. So if you have a question, you can raise your hand, and we will unmute you. And please try to be precise. Meanwhile, I can take some questions from the chat box, and I think some
trying
of
to
them have
see.
been answered by the later part of your presentation. So
Okay.
one is that a couple of, I think, repetitions. One is that did the helium originate in Big Bang, or did they synthesize in stars?
Okay, most of the heliums was synthesized during the first 3 minutes after Big Bang.
Okay. So the next is, I think the summary is that, since these elements are converted to heavier elements in stars, would the chemical composition of the universe change as a function of time?
It does, absolutely. It does. And so there's a whole field of chemical evolution of galaxies of the universe. And yes, absolutely right. So stars produce newer and newer elements, heavier and heavier elements, and then they throw them out, some of the stars at least, throw these elements out in space, from which new generation of stars are produced, so which are more chemically enhanced. The abundance of these elements are enhanced. So yes, there is an evolution of this abundance of heavy elements, yes.
Great. So there are, I think, a couple of questions on this nature of doing the measurement without the eclipse. One is, can you explain how Janssen was able to see the spectrum with a slit on a non-eclipse day?
Right. So remember what I said. I mean, you have to actually know the position of a prominence, because the slit is not so small, right? So you need a certain object to cover your slit. So you need a prominence. And as Lockyer had problems finding the prominences, but Janssen, during the eclipse, the prominences stand out. And so you can actually clearly see the prominence. So he had actually seen the prominence that day on 18th August. So he was just hoping that he had done some mental calculation. Well, how high are they likely to be? And so are they going to last for hours or days? He had done some mental calculation. So he was hoping that it would last for at least hours, so that or half a day, so that the next day he would be able to capture one of the prominences. And he did.
Okay, thank you. Anushka, do you want to ask a question?
Yeah, can Professor Biman please explain the concept of dark lines again? I didn't understand it.
Dark what?
Dark lines.
Oh, dark lines. So basically, you can think of it this way. The core of the sun, which is very, very hot, is emitting all kinds of lights of all colors. Okay. So if we could look at the spectrum of the light that is coming out of the solar core, it would have just all the lines, all the light, all the colors from blue to red, right? But then what happens is the light passes through the surface layers, the atmosphere, and the atmosphere is relatively cooler than the core of the sun, which is at, say, 15 million degrees, and whereas the surface layers is a few thousand degrees. So that's relatively cooler. So what happens is this relatively cooler gas, the elements, they absorb certain colors, certain wavelengths. Okay, and so those lights are absent when you see the spectrum of the sun from the Earth. So you see a dark line there. There's no light in those particular wavelengths.
Oh, okay. Thank you.
Okay, there is a question on how did the discovery of helium help astrophysicists to understand or discover new phenomena? Has this happened?
Well, I mean, this basically opened the window that, first of all, you can ask this question and find out what is sun and what other stars are made of, right? And once you start asking those questions, then you can say, well, the structure of the stars, for example, right? You have once you know what is it made of, then the next level of question is, how hot is it? Is there structure in the sense that is it all uniform, or is there differences in the density and temperature in the core, then the surface, etc., etc.? And then you start talking about the physics. And that's what astrophysics is all about. So it just opened the window to all these questions.
So connecting the astronomy with physics that you can do in laboratory in some sense.
Right. Right.
So Akash Chaudhary, do you want to? Akash Chaudhary, do you want to ask your question? Okay, I'll take another question in the chat. Does a white body exist in principle just as a black body?
Black body, it's just a theoretical construct. It's a black body is also a white body you can think of.
Yeah.
Black body, as I said, it absorbs all radiation, so it also must emit all radiation, all colors. So, black body is a sort of an unfortunate name associated with it. It creates all kinds of confusion.
Yeah. So Giridhar has one question. Will there be any radiation loss when light is traveling from a distant source like galaxies?
Yes, if there is intervening medium, then that some of the light will be absorbed out. So there will be radiation loss if there is a intervening medium. But if there is no intervening medium, then there will be other effects. If the galaxy is very, very far away, it started, if you talk about the evolution of the universe, expansion of the universe, then there will be other differences. Then the light will have a different wavelength. There'll be redshift, what we call the redshift.
Yeah. So there are a bunch of questions, which I think the summary is that, why do you need to really wait for an eclipse and look for absorption lines? The same element would produce an emission line during the normal time also. Why don't we look for that emission line?
Right. So this emission line, so that was Kirchhoff's idea, right? But those emission lines which are coming from the outer layer, they are basically.
Oh, sorry. I think the other way around. I think the question is the other way around. Why do we need to wait for the emission line, but not just look for the absorption line during the non-eclipse? So why do you need to wait for an eclipse? Why do we need to wait for an eclipse to look for emission line? The same element must be producing an absorption line during the normal time. So why not use that line?
Well, first of all, that was Kirchhoff's idea, but you have to actually test the Kirchhoff's idea that yes, this absorption lines correspond to the bright lines. That idea had to be first confirmed. Once you confirm that, yes, then you can go on to do this. And that idea, that confirmation of Kirchhoff's idea needed this experiment of eclipse. So first, just isolate the outer layers. Can you see the bright lines exactly the same position of the dark lines? Then one would know that Kirchhoff was correct. Yes.
Akash, do you want to ask your question?
Hello, sir. Am I audible?
Yes.
Thank you, sir, for the lecture. Sir, my question is, sir, like when some lines were absorbed by the environmental, or we can say atmosphere, when it is coming to us. So, sir, the elements also will emit the radiation corresponding to some wavelength, like not maybe the same as the absorbed, but so, sir, why can't we see them as also instead of the dark lines?
Yeah, so that's why I said, so if the matter is in thermal equilibrium, Kirchhoff had this idea that absorption and emission efficiencies are related. Of course, it is. It's not that it's just absorbing; it's also emitting. You see the result of both. But if it is relatively cooler, you will see the dark lines.
Okay.
But actually, you are actually seeing both of the lines. But how dark is it going to be depends on the circumstances of its temperature, etc.
Okay, sir. Thank you.
Okay, there is another question on YouTube from Arindam Connor. So the Earth has an atmosphere.
Yes.
So aren't there any dark lines
Absolutely. So
due to that?
Yeah. Yes. So Janssen had actually proved that there were some lines in the Fraunhofer set of lines which were due to our Earth's atmosphere, which I said they're called telluric lines, and he confirmed that by going up Alps and seeing less of those lines.
I don't know if I've missed any questions. If I have, please raise your hand and ask that question.
Okay.
Okay, Arush Murali.
So once the hydrogen and helium is used up, and in the star's core, all the heavier elements that if you fuse, it will use energy. For example, iron or magnesium. So why can't the star initiate fission to sustain the process?
I
And if you
couldn't
keep
get the
alternating.
question. There's some disturbance in the background. Can you repeat?
Oh, sorry, sir. When the star's core is full of heavier elements that do not yield much energy through fission, why can't the star actually use, fusion, and why can't the star use fission after that? So it will get more of the hydrogen and helium, and it can make like a cycle.
Again, I'm sorry.
So I think the question is, once once the heavy elements are synthesized, why don't they go back to the original elements by means of fission?
I'm sorry, I haven't really understood. Can you say that again, Ajit?
So once the heavy elements are produced during due to fusion, why can't those elements go back to the lighter elements by means of nuclear fission?
Oh, fission. Oh, yeah. Okay, but yeah, but for fission you require other things. I mean, you have to actually first break it, and for all, by the way, not all nuclei are amenable to for fission. There are fissile elements, right? So it's not that you can just break open, because depending on the binding energy of nuclei, your ability to go through a fission is determined by the binding energy. And it's not easy to just say that, once I have made helium or carbon, then I can just make, the carbon is not a fissile material. And also you need to strike with sufficiently energetic particles, etc., etc. Whereas the condition for fusion is the conditions inside the star, the solar core, stellar core, is conducive for fusion.
Okay, there is another question which is, I think, partly raised from confusion. One is, how exactly the spectrum is created and how Doppler shift affects the spectrum, and how can we be sure that the spectrum is accurate?
Doppler shift does change the wavelengths, and that's taken into account. But the Doppler shift, for example, you can say that the surface layer, the gas is not static. There is some movement, yes, but we know the typical speed, and so we know how blurred the lines are going to be. So depending on that, that determines the accuracy. You're right.
Okay, and there is more of a philosophical question, as the person admits, is it important to really credit the people who made the discovery? Because what is important is just the discovery.
Absolutely, I totally agree with you. Science is supposed to be impersonal, right? It doesn't matter who discovered what. And in a way, when one studies the history of science, I'm not so much interested in finding out who did what, but it actually, I find this, it's a story, it says something about us. It's a sociology of scientists. The way we view science and what have been done, and the way we record the activities, that says something about us. So I view science history, the history of science, as an activity less about history of scientists. It should not be about that. it should be about how ideas evolve, how ideas you know are recognized, etc., etc. But you are
So
right.
so it's a different kind of knowledge that is
Yes.
not about
Yeah.
nature, but about us.
Yeah.
Okay, maybe the final question. So, what is the best way to solve scientific disputes?
Uh, well, I mean, to just go through the primary documents. What I was surprised to find is that people always depend on secondary sources. And my first surprise was when I started looking at Jansen's original papers, and I found that there's no mention of a new line. And I realized that everybody was depending on secondary sources. And that's, I think, it's a lesson for me in studying history. You should always look at the primary sources. And I think it should be true in when we do research also. When we look at a paper, the paper may say, oh, somebody has done this. And we should not just take that for granted. We should actually look at the primary sources and see. And that was a lesson for me.
Yeah, that's a great lesson, Biman, and I think probably it's the right time to stop this event also. So thank you very much for this, for taking us for this journey. This wonderful combination of science and history. Thank you very much, and thank you all. And we look forward to seeing you in the upcoming events of the Cosmic Zoom. The full list of events will be periodically updated on the Facebook page as well as the website of Cosmic Zoom. So it's cosmiczoom.in/events. The next event is the day after tomorrow, March 31st. And that is a conversation with two evolutionary biologists, Amitabh Joshi and TNC Vidya of the JNCSR. And this will be hosted by Bertie Ashley. And the discussion is on why size matters and how behavior and the architecture of various organisms around us are basically shaped by the environments. I look forward to seeing you there in a couple of days. And meanwhile, take care and thank you very much.